In the field of probabilistic forecasting, the industry has placed heavy confidence in deep neural distributional models. Architectures like NBEATs and NHITs are deployed as the standard tools to map out future uncertainties. This heavy reliance on neural structures has created a blind spot. Evaluation protocols for new, complex models systematically skip over low-compute, transparent baselines. We can audit this directly by examining Deep NPTS, a highly cited non-parametric neural sampler that was originally tested against the Gluon TS reference suite. We are running Deep NPTS head-to-head against a baseline algorithm called Conformal Seasonal Pools, or CSP. CSP contains 0 learned parameters. It requires 0 training. Testing these two approaches side by side reveals that the automatic assumption of neural superiority is masking severe defects in how predictive uncertainty is actually calculated. This chart plots 6 forecasting methods by mean CRPS rank versus computation time. In the top left, green CSP markers operate in the training-free zone, finishing in under 1 minute with top-tier accuracy. On the far right, the isolated red dot is Deep NPTS. Deep NPTS takes 153 minutes to complete the exact same workload that CSP finishes in under 20 seconds. That is a 567 times slowdown, and it results in a worse mean CRPS score. Burning hundreds of times more compute to generate a less accurate forecast indicates a failure in the model's core logic. Probabilistic forecasting operates on a strict rule set established by Tilman Gneiting and Matthias Katzfuss. A forecaster must maximize sharpness, but strictly subject to calibration. Calibration is the absolute prerequisite. If you generate a hyper-narrow prediction interval that fails to contain the actual ground truth, that sharpness is mathematically useless. It is simply narrower wrongness. Deep NPTS fails this exact prerequisite. When tasked with generating a nominal 95% prediction interval, its empirical mean coverage is only 66%. As the distribution drops, a massive portion of the data falls entirely away from the 0.95 target line. When we overlay the CSP adaptive baseline, the contrast is stark. The training-free model tightly clusters safely near the 95% target line, averaging 89% empirical coverage. A nominal 95% prediction interval that misses the truth roughly a third of the time is actively misleading any downstream operation that relies on it. Any model failing this basic calibration desiratatum is immediately disqualified from deployment in decision-critical environments. The aggregate average of 66% hides a much sharper operational hazard. In the worst 10% of forecast windows, the lower decile, Deep NPTS's coverage drops to exactly 0.03. At a coverage of 0.03, the neural network is completely blind. The model plots a multi-step trajectory, and the shaded 95% prediction interval veers so far off course it fails to intersect the ground truth line across the entire horizon. The missing 34% of overall coverage is not distributed as thin, occasional misses. It is heavily concentrated in these total, simultaneous trajectory failures. In heavily regulated or physical domains, these consecutive errors stack rapidly. A trajectory prediction that systematically misses the truth triggers Basel III capital requirement failures in financial institutions and causes immediate reserve capacity shortfalls in power grids. In safety-critical applications, mathematical miscalibration translates directly into regulatory violations and cascading physical system failures. The fact that Conformal Seasonal Pools avoids this failure mode without training a single parameter comes down to its mathematical structure. CSP begins by generating a seasonal naive forecast. It identifies the target horizon in the future, then traces back to find the exact corresponding position on the previous wave cycle. The algorithm then builds a seasonal empirical pool. It groups historical points that share that identical seasonal phase across older cycles into a distinct container, applying exponential recency weights so older data fades in influence. However, relying solely on empirical pools creates a vulnerability. They are entirely blind to sudden level shifts in the most recent data. To correct this, CSP constructs a signed residual pool. It measures the exact gap, the residual error, between the most recent actual points and their naive predictions. These error measurements are deposited into a second container to capture recent shifts. Finally, CSP draws equally from both containers. By applying a 50-50 mixture weight, it generates a densely populated, well-centered cluster of prediction points around the future horizon. The algorithm also contains an adaptive rule. If the time series lacks seasonality entirely, CSP zeroes out the seasonal weight and seamlessly reverts to a pure conformal residual sampler. CSP solves the calibration problem using historical geometry. It uses conformal residuals to center the data and empirical pools to shape it, completely bypassing the need to train a neural network. The rolling origin benchmark tracked performance across 6 distinct GLUE-TS datasets, covering everything from electricity and solar energy to traffic and exchange rates. Across all 6 datasets, CSP Adaptive consistently hits or exceeds the 0.95 target line. Deep NPTS undercovers on every single one. We evaluate predictive distributions using the Continuous Ranked Probability Score, or CRPS, which penalizes tail miscalibration. Paired Wilcoxon tests reveal massive significance. CSP beats deep NPTS on CRPS, quantile loss, and coverage, with p-values resting at 10 to the negative 10th power or greater. These margins rule out any benchmarking anomalies. The training-free model statistically annihilated the deep learning model on the exact datasets used to originally validate it. The final equation is clear. The conformal baseline achieved superior accuracy and calibration in under 20 seconds. The neural network spent 2.5 hours generating narrower wrongness. Data science evaluation protocols must adapt. Training-free conformal samplers like CSP must serve as the mandatory baselines in all future forecasting benchmarks. If a highly parameterized neural model cannot beat a zero-parameter empirical mixture on strictly proper scoring rules, it has no business being pushed to production. In probabilistic forecasting, algorithmic maturity is measured by the mathematical discipline to honor the truth of uncertainty, not by parameter count or compute time.